compute the integral along the curve C of vector x comma negative y dot dr, where the curve C is a line segment between 2 points. So this is what's called a line integral. We have, as the integrand, we have a vector valued function of the variables x and y, which typically has the form, it's a vector, and it's going to have 2 components. We're in R2 here. We have a line segment between these 2 points in R2. So it's going to be a vector in R2 of the form, first component will be some function of x and y, and second component will be some other function of x and y. And in our case, the function f1 of xy is just x, and the function f2 of xy is just negative y. But in general, the first component here and the second component are functions of x and y. So you might see x's and y's both in each component. So this is a fairly simple function, vector valued function. And the line segment, C. So in order to compute this, we have to parameterize the curve, in this case the line segment, by some function r of t, where t goes between 2 values a and b. And then we integrate from a to b, and the r of t has the form x of t, it's a vector, it's the vector, the position vectors of each point on the curve. It has the form x of t comma y of t. So this represents a point on the curve in position vector format. And so we need to substitute into our function where every x will be replaced by x of t and every y will be replaced by y of t. So we'll have the vector function with x of t comma y of t. And then we have to dot this with dr. R prime of t is the vector x prime of t comma y prime of t. X prime of t, y prime of t, and dr will be r prime of t dt. So r prime is a vector, just like r was a vector. And so we have 2 vectors here, and we have a dot product. So this is going to give us an ordinary function of the variable t. So let's see what happens in our particular case. Let's parameterize the line segment so that we can figure out what x of t and y of t are. We need those to plug in here and here, and then we'll calculate r prime of t. So a line segment from a point, let's call this point P, to a point Q has the form, if this is P and this is Q, then the form of the line segment from P to Q will be, we'll take the point P in vector form plus t times the vector PQ. So in our case, that means that r of t is the vector 1, 1 plus t times the vector from P to Q. So we take the components of Q and subtract the components of P. So negative 1 minus 1 is negative 2, and 0 minus 1 is negative 1. So there's our line segment, and t goes between 0 and 1. If t is 0, we get the point 1, 1 where we're starting, and if t is 1, then put 1 here, then we get 1 plus negative 2 is negative 1, and 1 plus negative 1 is 0, so we end up here. So that looks like it's correct. Let's combine this. So r of t is equal to the first component is 1 minus 2t, and the second component is 1 plus t times negative 1, that's 1 minus t. So this is r of t, and that means that x of t is 1 minus 2t, and y of t is 1 minus t. And t here goes between 0 and 1, as already mentioned. And r prime of t, take the derivative of each component with respect to t, we get the constant -2, -1. That's r prime of t. That's the tangent vector to the curve. Okay, so this format becomes integral. A to b is 0 to 1. T goes from 0 to 1. And our vector here, we have to substitute x of t and y of t in. So we have, instead of just x, we have x of t. X of t is 1 minus 2t. And then we have negative y. Y of t is 1 minus t, so negative y of t will be t minus 1. And we have to take the dot product of that with r prime of t, which is the constant vector -2, -1, and then dt. Let's compute this dot product. Just a dot product. And we get -2 plus 4t, and then minus t plus 1 dt. Now we get a basic integral in t. It's 3t minus 1 dt. And we can find the antiderivative and plug in the numbers. If we plug in 1, we get 3/2 minus 1. And if we plug in 0, we get 0. So this is our answer. 3/2 minus 1 is 1/2. And that's our line integral. Woof.